All right, now I want to find the open intervals, once again, where our particle is speeding up and where it's slowing down. And just a reminder, people see speeding up and slowing down and they think acceleration, but acceleration is the derivative of velocity. I did not say velocitying up and velocitying down. I said speeding up and slowing down. Speed is the absolute value of velocity. So remember that in order to determine where a particle is speeding up and slowing down, we need to look at both the velocity and the acceleration. What we determined is that the particle will be speeding up if those two functions have the same sign. It will be slowing down if those two functions have the opposite sign. Okay. If velocity is positive, it's the same thing as speed, and so speed increases if velocity increases, which is acceleration is positive. But if velocity is negative, to be speeding up means that the absolute value of the velocity would be increasing. And for negative numbers, the absolute value increases as they become more negative. So we would need velocity to be decreasing in that case. So we already, in the context of finding the distance, created this number line to record the sign of the velocity. What you're going to need to do is create another number line to record the sign of the acceleration. And then I usually like to just create a third one to compare the signs of the two. And where they have the same sign, the particle will be speeding up. Where they have the opposite sign, it'll be slowing down. Okay, so pause the video and try to answer these questions. Okay, I cleared some space here so we'd have some room to work. Acceleration this time is not constant. Acceleration is negative sine of t. Now, that is always defined. So the only times that the acceleration could change its sign would be if it passes through 0. So we'll set negative sine t equal to 0. Now, of course, that has infinitely many solutions, but it only has finitely many solutions in this interval. This would mean if t is equal to 0 or pi or 2 pi. Now, 0 and 2 pi were already the endpoints. Okay. So the only new point I need to mark off is pi. Now, although I didn't draw this to scale, I am going to make sure that everything is consistent with that. So here is where 2 pi over 3 is going to be. Pi is in between 2 pi over 3 and 4 pi over 3. Okay, so now I need to figure out the sign of the acceleration over each of these two subintervals. Now from 0 to pi, I know that just corresponds to quadrants 1 and 2. In quadrants 1 and 2, sine is positive, but acceleration is the opposite of sine. So acceleration will be negative. The interval from pi to 2 pi corresponds to quadrants 3 and 4. Their sine is negative. That will make the opposite of sine, which is the acceleration, positive. Okay, to compare them, I want to mark off all of these places, 2 pi over 3, pi, and 4 pi over 3, all of these places where any one of those functions changes sign. And to make it easier to see, I like to just fill in each subinterval with the appropriate sign. So then I can see from 0 to 2 pi over 3, velocity is positive, but acceleration is negative, so we've got the opposite sign. From 2 pi over 3 to pi, they're both negative, so we've got the same sign. From pi to 4 pi over 3, we've got a negative velocity but a positive acceleration, so we're back to opposite signs. And then from 4 pi over 3 to 2 pi, they're both positive, so we've got the same sign. All right, so that's going to allow me to state my answer. We would be speeding up on the open intervals where we have the same sign. So that would be from 2 pi over 3 to pi, union from 4 pi over 3 to 2 pi. And then we would be slowing down on the open intervals where we had the opposite signs. So that would be from 0 to 2 pi over 3 union pi to 4 pi over 3. And here, even if I wanted to, I wouldn't be able to include 0 and 2 pi because those were places where the acceleration, remember, was actually 0. So it didn't have the same or the opposite sign of the velocity.